Friday we went over heat treatment in a very condensed way. So those of you who were not here, I do recommend you watch the video just because it was pretty condensed. If you fall asleep, you'll have to rewind it. I went through aluminum and steel. Yes?
It wasn't up yet by yesterday afternoon.
Okay, yeah. Well, we will essentially continue. And, you know, I always like doing this because I know you guys don't really have a quiz, so I do try to go back a little bit to the last lecture. So what we learned on Friday is there's a huge difference between aluminum and steel in terms of the heat treatment. So what I explained is with aluminum, what you try to do is form these very tiny precipitates inside the aluminum matrix. So it's precipitation hardening, and the way to do it is you heat it up, and just like everything at high temperature, you have more solubility. So if you have copper in the aluminum, if you have magnesium, they all come into your crystal structure as a single phase. Now, if you cool very quickly, they don't get the chance to diffuse, agglomerate, and form the precipitates, so nothing happens. And it's when you do the aging process, which essentially is eating up at relatively low temperature, is when you start forming the precipitates, and you can see here that the strength's going up over time. So it's very particular to aluminum that the quenching itself doesn't make it hard. On steel, on the other hand, if you cool it quickly, and actually on Friday I did not have a good image of the microstructure. When you cool quickly, you have iron face here, the white grains that are very soft, and then you got this perlite that's a combination of cementite, the little carbon iron combination, that's the black, and then there's white into it. So this face here grew by diffusion of essentially moving the carbon between two layers of iron-rich face. So it grows very slowly this way. It requires diffusion. It's a little bit like our dendrites when we were talking about solidification. But it's a solid-to-solid transformation, so it does take a lot of time. So to some extent, it's difficult to avoid dendrites when you cast. You can do it, but you know, we talk about essentially having a very high cooling rate. It's relatively easy, on the other hand, to avoid having this transformation. So if you cool very quickly, if you quench, you end up with what we call Martensite. And we went through the details Friday, but essentially it's a structure that's very hard to deform. It's not very symmetric. So when you're thinking about having the movement of dislocation, there's not many ways for the dislocation to move in there. So it's very, very low ductility. We do not use it for structural application other than tools for machining and kind of cutting tools is where you can have you know, a Martensite structure. So perhaps I bought these last time and I didn't try them. I don't know which one is which. There should be one here that is ductile and one that is not ductile. So we'll see what happens. Oh, no ductility, right? It just snapped on me. And I mean, you'll see, we'll circulate it around, but we don't want steel to behave that way. It's a little bit like glass. Let's try this one. So this one is the polycarbonate, and the other is the acrylic. Well, I want you to remember, because even you talk to engineers sometimes, like, well, ductility, you know, it's, you know, I don't know, it's kind of like it deforms. Yeah, it deforms before it breaks. And now, if you touch it here, and you can play with this one, just be careful. Sometimes it may separate in 3 pieces. You can see it's hot because of the deformation. Yeah. So It's very difficult to have a problem with aluminum of becoming from something very ductile, very tough to something brittle like this. But with steel, that's the problem. If it's quenched, it will behave a little bit like the acrylic here. So you have to essentially work on doing a tempering. So you use this structure and then you heat it back up, but as opposed to in the aluminum, when you age it, it becomes harder. In this case, it becomes softer. So you essentially go back to more the equilibrium phases, and that's where we can use essentially heat-treated steel. And we'll see some examples of that today. I'll talk a little bit about surface modification. I brought a self-drilling fastener for that. And then we'll start talking about welding. Welding, hopefully, we spent at least a lecture and a half or 2 lectures on it just because it's very useful. And I think I can give you a good overview. I've seen enough how it gets specified, how it gets used. I'm bringing this one up because, to my knowledge, in terms of a structural steel, the pre-stressed wires here are those that are used with the highest yield strength. So in terms of heat treatment, it's heat treated to a very, very high yield strength. And the reason is, so the way this works, these cylinders can be, the one that I inspected were up to 16 feet in diameter. So higher than the ceiling here. And it's very high pressure. You talk about 500 psi pressure for water distribution to the main cities. The one I most worked on was in Chicago. And a lot of time, there's not a whole lot of redundancy. I don't know if you guys were around Cambridge area where we had the big break in Weston. And the water we didn't run out of water for more than maybe a couple hours, but then they worried about contamination, so everybody had to run to the store to get some bottled water for drinking. Must have been maybe 5 years ago, so maybe a few people were around here. But it's essentially affected all of Boston, many towns in the suburbs, except Cambridge, which has its own water treatment facility. But it just speaks to how we oftentimes rely on just a very few structural items. Now, it's engineered. So the way these cylinders for potable water work is there's a concrete core. In this case, it has a reinforcement. So just a little bit like the floor here. The main difference is after you build that concrete cylinder with reinforcement, you wind around these pre-stressing wire, and they essentially put the entire cylinder in compression. So the real structural element here is a very small wire. I mean, I'll draw it to say it's a very specialized field, but literally about this big. That's it. Now, there are a lot of them, so we show them here. They can be spaced just about 1 diameter distance, so just like this. And you have them going over, if it's 4 feet, 6 feet, 16 feet in diameter, and as you wind it is when you put the tension in it. You just wrap it, and that's what puts the inside on a safe zone. But there's a second aspect to this, which is not only you compress the cylinder, but when the pressure comes, those wires are the first one to resist it in tension. They don't want to grow in tension. So it's used in very high quantity. And when I was talking about strength here, and I'm sorry, I'm going to have to use KSI this morning. So if we're thinking about a basic structural steel, we're looking at a yield strength of 36. That's pretty standard for a building. Those can be, there's a 180 grade. That's old school. There's a 225 and a 250. So we moved up by a factor of 8 or so in strength capacity. And essentially, by going to this heat treatment here, instead of having something that's a perlite, it's the same composition, same alloy. But instead of going to this perlite, you go to the Martensite and you temper it a little bit, and then you work it also, you cold work it. So this material is pretty much the hardest you can have. It's not spring steel yet, but it's closer to spring steel than anything else. Now, why are we doing this? What if one of them breaks? Nothing, right? So there's a lot of redundancy in the system. They start talking about having a problem when they have about 15 adjacent wires that are broken, just the way it's built. And yes?
How do they manufacture this? Is it one step or?
The wires?
No, like the whole structure.
Oh yeah, you have to cast the cylinder, you let it age, and then you bring it to the winding.
Oh, so you wind it after the first.
Yes. It's a little bit. It's a little bit like what sometimes we'll call the concrete post tension. So you build the concrete, and then you have the big strands or the bolts going through it, and you tighten those after the fact. It's just a little bit the same effect that you're getting here. Yeah.
There's not a single wire, it's many different wires.
It's the same wire that keeps going around, but there is a lot, it's embedded in grout. So there's a lot of shear resistance. If you break it, it's not going to unwind very far. The concrete will stop it. Good question. Now, this is all nice, right? Because we're having all our wires that are resisting essentially the hoop stress. These cylinders don't really have tension. If you remember your basic mechanics, if you have a closed cylinder, you're going to have a stress this way that's only 1/2 of the hoop stress. If the ends of the cylinder are free to move, there's no tension. They can just go back and forth. So they make the joints of the cylinders essentially a bell and spigot, they call it, so that there's going to be a member on the outside. Looks like this. Then you have a member on the inside coming in. Inside. Then you put a big O-ring in here. So it's able to move a little bit. Now, of course, you need mechanism so it can't go too far on the long scale. So when you get to a turn, you have all these restraint blocks, and it's a pretty sophisticated system because you have more than 100,000 pounds at each joint being transfer or not transfer. The leak we had here in Massachusetts from MWRA was not the cylinder itself. Yes?
I was going to ask, how do they support the pipe without putting it into bending? Because they have to put something underneath it, or do they just sort of trench it around?
From here to here? Yeah. Well, yeah. So when they excavate, they have to put a pretty good base that's pretty straight. So when they lay those pipes, they line up. But it's a very good question, and they do put a clamp. The reason you put a clamp is if one moves, you don't want it to disengage as opposed to the other. So you want some flexibility, but in reality, you don't want these things to go very far. So I'm showing a clamp here, and that's actually what caused the MWRA break. A big steel clamp that was connecting those two pieces together on the outside. What exactly happened is what you said. There's bending between the two cylinders. Not so much from the original installation, but settlement in the ground. And then, of course, it was very difficult to verify exactly how bad the settlement was because you had a big washout. when the clamp failed. So you can essentially expect, but by the failure mode, that it was related to ground settlement, but there was very hardly any way to verify it. I said I was going to bring in a few failure analysis cases. So this is one from the Chicago area where it failed during pressure testing. So that was a really good effect because they didn't, it wasn't service interruption. It was a new line that they were putting in, and they were still energizing it and testing it out. And it failed again at the joint. And that's a topic that you'll hear me say a lot of times: joints, joints, joints. Do you find out if you have heat treated welded? Okay. So the joints tend to be elements of more failures in general than the members. So with respect to that clamp, when it was that 16-foot diameter pipe that I was talking about, and I could see this line here. I'm sorry if I don't have any better picture of it, but essentially looking into the clamp, which was essentially really a C-section. So we have something like this that is intended to go right over the two sides of the pipe. So you have one pipe engaged here, one pipe engaged there. It failed here. I'm trying to think. Yeah, it failed this way. That was the crack. So now we're looking at this fracture here, and what you see on one side is, if this is the pipe wall, I see this line. What kind of line do you think it is? We only seen two. We've seen the crack propagation and the crack arrest line. The true, we have both. So let's fix this here. I'm going to help out a little bit. There you go. Now we see that we see both, right? So that's propagation and that's the arrest. So from that vantage point, they already had it cut it up, by the way. So it was always more fun to figure out what's going on. But by this general shape, I know my initiation is this way. So there was a pre-crack essentially before reaching the critical strength of the material. And right over here is where I went to look, do I have an inclusion? Do I have something like a notch, a rolling defect? Do I have anything that can explain why the crack started here? And there wasn't any. In fact, what I saw here is the bearing mark against the pipe. So the pipe is here, was only over here. It was showing here on the tab as opposed to all the way to the inside, very close to the joint. So from this indication of contact between the end of the pipe and the clamp, I essentially determined that this clamp was not fully engaged into the pipe, and that's why it broke. It looks simple, but you have to be looking exactly. This mark was the furthest from the corner here at the position where it broke, and then it was going to a higher engagement at the other location. So the clamp was not sitting square. Somebody decided that it was good enough. They went on and they put some grout to protect against corrosion. The think we're good. Then they had a failure and they had to go back. The problem then is somebody always asks, okay, so it failed. So how do I know it's not going to fail again? Well, the answer in this case was good, because you say, well, we're going to check that the clamps are put on properly. If it was an issue with the clamp itself not being big enough, not being strong enough, then that's a bigger problem because they have to undo other joints that were already there. So they actually went back. The good thing is it wasn't refilled yet. So they took the grout out all the other joints to check that the bolted connection were fully clamped. So they didn't have to go all around. They went to each side, but verified that there wasn't any problem. So it's one of those examples where it happened on a Thursday, and we were there the Friday morning, and then the Friday afternoon, they were just checking it because they had to refill and move on to other things. Yes?
What was the reason that the clamps weren't pushed out of the way? Was there something in the way?
I think it's a good question. I think that they were probably just having a hard. The two pipes were a little too spaced, and there's a little bit of a tilt here, so you can hope for the clamp to bring the cylinders back together, but it's a big hope. So they essentially applied full torque, but they couldn't get it in, and they just moved on because the solution was to use the crane tool to bring the two pipes closer and then try to do the connections.
So is that what they did once you discovered the problem?
They essentially had a damage to this pipe, to this one, so they had to take the two pieces out, bring them to the shop, and redo them. So nobody was happy. But to some extent, it's a little bit where it was a great service for the contractor to have us on call because they were not generating as much worries in the part of the city and everybody involved with the project. They really worked over the weekend to make sure that they were not going to have any delays. I wanted to bring out some more examples of where we used and this was also quench and tempered because you don't need to weld it. It was a single piece that was, I believe it was machine and then form into this half clamp shape. And part of that reason is probably just volume. So if they were making a large quantity of the exact same shape, they would try to forge it. But this one was machine. And actually, I wasn't very happy that they didn't really have a big rounded corner here. But there's only so much I could do about it because if it was fully engaged, there wasn't much bending forces, so it should not be a problem. But at the same time, there's no reason not to round the corners in a design like this. So other example of high-strength steel being used, quench and tempered, all the drilling industry really, whether it is drilling operation or cementing, fracking. So this may or may not come back a whole lot, but I did work for Schlumberger, and I've been doing a lot of failure analysis related to drilling. So I can tell you a little bit about it, so this puts you a little bit in perspective. If you're drilling, you go through a lot of different sizes. So say you're making a big well, a big hole first, then you do a smaller hole, a smaller hole, a smaller hole. So if you start here at about 2 feet, you may end up at 4 inches at the bottom, just by the virtue of having to continue to bring the fluid in and clean it up. So in the drilling operation, you have two things that are important. I have my drill string here that's rotating and it's feeding the bit. So it's bringing fluid down on the inside, and on the annular space, I'm bringing all my drilling debris out. So I'm circulating mud from the inside out as I'm drilling. So those strings, essentially, you'd want to have a very good tolerance on the inside and the outside, especially when you're becoming small here. There's just no extra room. So you need very high strength, high quality steel for this application. Of course, if you're going 20,000 feet is pretty typical, so 5 miles down. You, of course, bring the steel into pieces, about 30, 40 feet long, and then here are your threaded connection. But if you look at this piece here, if you remember when we were talking about forming and deformation processing, you could potentially forge it, okay? I'm not saying it's impossible the same way we did the bolt. We just pushed it in and grew the diameter, but here we have to keep in mind it's a tube. So it's empty on the inside, and when I push, I need to hold the inside, I need to hold the outside. So I don't think that at this point there's not a whole lot of forging operation done to make these strings. The way they do it is they manufacture the ends and then they fusion weld it to the plain pipes. In the sequence of work, if you will, this is a friction weld, so essentially one piece is rotated with respect to the other. It provides enough heat, and then it's being pushed one against the other, and you can see the excess metal showing up. It's a good quality joint, but it is affecting your microstructure of the steel. So the way they work this is they make the joint, and then they do the heat treatment. And they get rid of that brittle phase, because if it wasn't for that, then you have a very brittle zone somewhere between the fused metal and the base metal. They make a large quantity of these, and it turns out that these joints sometimes are over and offset, and I think that's the case here. So this section is a slightly bigger diameter than the nominal diameter of the pipe. So that helps a little bit in having a little less stress over where you have that transverse joint, even though it's a good quality joint. What else did I say? So in the grand scheme of our strength here, the P110 is a very typical drill string pipe. So 110 KSI is the strength. So you don't push it as much as you did with the wires, but you are about 3 times stronger than structural steel. Now, why are we limiting ourselves here? The main reason is you will encounter some pretty aggressive environments during the drilling. And if you push your limit too high on the strength of the steel can become susceptible to environmental cracking. So this limit here is actually very, very close to the maximum where you'll start having problem of stress cracking in service, and you of course want to avoid that, because when you're 5 miles down and it breaks, now they have to bring the fish tool and pick it up, and it's every day on the rig is very expensive, so they try to avoid that as much as possible. Okay, another type of joint that to us will probably look easier to do. So you have the 2 plain pipes, you put a tread to it, and then you put a collar. That's done for, I would say, less demanding situation. After you drill, you put these casings into the well and they'll stay there. But the only thing you need to do is to get it in there and then manipulate it a little bit. You'll use it for the fracking operation. I'm not saying there's no demand on it, but it's not really a drilling tool. And that's why they do afford. You could think of it like this joint in tension will definitely have less strength than the pipe itself, because you have to machine out material to make the tread. So it can't be as good as it was before. So when we see those fail in the joint, it's not a big surprise. Now, one situation we've seen that was, I guess, unfortunate for the industry is we did see a whole lot more failure on the coupler here than the pipe itself. And the coupler does have a little bit, it has the right amount of material. In other words, if the coupler was made as good as the pipe, there wouldn't be a problem. But somehow in the control process, and the people that manufacture those couplers were not really controlled in terms of quality. So I've seen cases where they exceeded this strength, and that caused brittleness. There are other cases of essentially different toughness of the steel that could have been tested beforehand, but people thinking of it as more of a consumable as opposed to a work equipment like the drill string. So it seems like there just wasn't enough quality control done on those. We're still talking about the same kind of strength in general. P110 is very critical. I have a project they were using 125 strength. Quench and tempered 125. It didn't fail at a joint. It doesn't seem to be related to the heat treatment, but it did fail. And, we're trying to figure it out, even though there's a, consequential damage from the failure, and sometimes it's difficult to differentiate between the two of them. We talked a little bit after the class about automotive. Automotive use a lot of welding, and they don't use, this is a good one. So they don't use, so we had here, so what do we have? So we had water. That's a good way to look at it. Oil and gas. So what do you expect? More failures, right? and then here. Automotive, a lot of the steel is going to be pushed to the limit where you can still weld it. So you get 65 is pretty standard. You can get up to 70 KSI is typical, and you still weld it. If you have components that you don't need welding for, then you go to the quench and tempered. But the automotive in general doesn't use a lot of quench and tempered steel because everything gets welded. So think of it this way. Every time that you want a steel that is going to be welded, then it needs to be a steel that doesn't get too hard during the heat treatment. That's pretty much the baseline. Now, let's talk about some of other applications, some other things we can do with steel. These are self-drilling fasteners used to make buildings really fast. So you see there's a bit at the end. You see it here. And then it's the tread. So in one operation, you perforate through structural steel and attach, and then you even have the seal. Pretty efficient way to do it. So you can circulate. On this one, you can see it's darker on the surface. These are cut sections. So what happens here, and that's interesting. So the P110, I'm just going to say this is HRC 35, just approximately. So it's kind of the harder steel you can have that is still not susceptible to the environment. A lot of times that's the hardness that you want to have in the core of that fastener here. But if you're going to drill through other steel, you want the surface to be harder. And one way to do it is put it in a high CO2 environment, and you do a carburation process. So you add carbon to the surface of the steel, and we can see it in some of these images. There's a little bit of a different light at the corner there, so we're not going to focus on it, but I want you to look between the center here and what's happening close to the surface. So this is approximately 100 micrometers, and that's what's on the surface of that fastener. It's essentially a way where you can almost double. So if you go from 35, 50, you really increase your hardness, and that becomes the same material, but just the surface is different. It's very much used for gears and applications where you want the surface to be very hard, but you still don't want the entire gear to break like our plastic here. So it's not good if you start cracking on the surface, but in some of these applications, you'll crack on the surface and it stops when it reaches the base metal. So that's a very desired situation if you're in a wear application. If you're really in a tension application, we don't use it very much. So we don't do that on landing gears, because if we do initiate the crack, it will continue. There's a reason why it started there. So it's mostly for wear, and in this case, it's just for the very beginning. So they were able to mask the other zone. They only hardened and put carbon on the end of that fastener. All right. Let's see. You see here the Martensite, but it looks a little different here because it was tempered. So there's still a little bit of a history of the needles that we saw on the quench composition, but it did go through a diffusion process after the fact to make it also ductile and tough. So that's really where the compromise is. Any question on the self-drilling fastener? It's used a lot.
Is it similar to what they do for like drill bits?
The drill bit, that's a good question. So the drill bit a lot of times will be low ductility through the core. And it will have additions like cobalt, and that will, and those elements, you can't just put them on the surface, so you're pretty much stuck with having it everywhere. Now, if it's a plain steel, yes, on a plain steel, you can put the carburation on the surface, and then you don't break them. So like a kind of a low quality bit, sometimes you can't bend it, right? And it's still surviving. Now, is it desirable? No, because it should have the cobalt and other additive tungsten to go from a hardness of 55 to 65 if you can, and a very special microstructure. They become composites. If you look at them under the microscope, there's as much of the secondary phase than the first phase. And that's really where you get your strain from. We'll go to fusion welding, just get started here, and I want you to keep in mind the main reason we're doing this is manufacturing, overall cost of fabrication. If it wasn't for that, we would probably avoid it altogether. The very traditional welding, also called stick welding or shielded metal arc welding, essentially use an electrical arc to eat both the consumable and the base metal. So we have our workpiece, and say we have our welder unit. You always need to ground what you're welding to. And if you don't do it and you're building something that has bearings in it, you lost the bearings because the current goes to the ground and welds everything that's in it. So say we have our workpiece, and for now we'll try to make a T connection. So it looks like this. So I prepared this component to come down to this with a bevel. And then I come with my electrode that is either positive or negative depending on what I'm trying to do. I get different fusion. And all I'm trying to do is from the time that the arc is taking place, I'm melting both ends of this. So the metal gets projected here. I get fusion of the base metal. And I'm left with a welded bead like this. So if I do it in one operation, it may look a little bit like this in terms of the fusion. So this is my weldment. You can weld, pretty quickly if you're trying to do a joint. One of the, I guess, practical aspect is the control of that bead. If you're trying to go up, if you're going overhead, gravity works. If gravity works against you, depending on the process you're using, the polarity, you can try the procedures where you're supposed to go up or down, depending exactly on what you're doing. But ultimately, you get this bead that is approximately, you try to make it regular, and you're done. Now, depending on the quality of the steel that you have here, or I should say, it's really the strength of it. You'll always have a heat-affected zone. So what we call this, we call it the toe of the weld. From the toe of the weld and anywhere around here, there's going to be this zone that was heated and cooled pretty quickly. So depending on the material you have, and I can be general here and do both aluminum and steel. If we're talking about aluminum, from what we've learned Friday, when we heat it up, if we heat it up enough, we go back to solution and quench it, it's very soft. So if I put the toe of the weld here, and this is the fusion zone, I can have a certain strength here that is based on my welding electrode. It can vary a little bit, but not a whole lot. Say I started with a pretty good, if you remember from Friday, we started with a T6, pretty good aluminum alloy in terms of heat treatment, and then it goes down, back up. So we got this because right next to the fusion, the material got to the melting point. And that's where all these little precipitates go back into solution pretty quickly. It's very hot. There's no problem for it. Now, our temperature profile here is going down, but as soon as you stop the fusion, all the heat goes into the base material. And what you'll see there is there's a big difference on depending, say, if I'm welding something here that, if I'm welding something that's, say, a 1/4 inch, so 6 millimeter thick, as opposed to 25 millimeters or more, the cooling rate in this heat-affected zone is going to be very different. Because you essentially have more material that remain at ambient temperature and the heat travels to it very quickly. So over here, this is mostly going to affect the spread on how big the divot is, but the low point is just essentially solution treated and quenched aluminum, so it's not going to change very much. Now the best news here for aluminum, it's still very ductile. Nothing happened. Now, when we try to do this with a relatively high strength steel, and try to put it in the same scale. So whether it was the P110 or what else we have, we can have a 4340, any kind of relatively high strength steel here is going to have a certain strain in the fusion zone. And then when you get to the toe, whoa, is where you get to your peak here. And then gradually you'll come back to the original strength. So over here, you got it close to the melting point and you cool it down really fast. So that's your Martensite here. And it's a problem in terms of ductility. So when I said that for a welding application, you stay typically in this range, is because the way these alloys are built is not by adding element that makes it easier to get into Martensite zone. It's just essentially very small amount of alloying element that increase the yield strength. Typically by solution hardening. We haven't really talked about solution hardening, but it's another type where the atoms stay in the matrix and just cause friction for the dislocation. Okay, if you see on campus, like we have a lot of welding going on, the blue light is damaging to the eye, so you try to avoid it. The spatters are also a concern. They don't kill you, but you can get some holes in your hands if you don't wear your gloves all the time. So it's not considered highly dangerous, but it does also create fume. So you can't do it in a confined space. They've gotten better in terms of the operation at having some good ventilation when people weld that because of their history. So historically, the welders were getting sick. So they decided to go and make some big improvements. Another aspect of welding that is probably intuitive, but I want to go over it with you, is if you heat up the metal, it will tend to oxidize, react with the oxygen. So you need to avoid having oxygen in contact with your welded piece. And when you go through all the welding processes, and there are many of them, they have a lot of essentially different ways to protect your fusion zone. There's nothing more to it. In the case of the shielded metal arc, there's a consumable here that creates what we call a slag. So it's an ionic liquid that goes on top here of the fusion metal, and it has a high affinity for oxygen. So if there is any oxygen in the weld metal, it will diffuse to that zone. So the activity of oxygen in the slag is much lower. So it brings all the impurities in. Now, you can probably see that even though this is a very, very simple process, when we go into more sophisticated and the cases where we don't have a slag, you become more at risk for the effect of the original cleaning of the surface. In this case here, it's forgiving because the slag essentially will pick up a lot of the impurities in the weld metal. So if there's rust on the first place, it will essentially be picked up by the slag as well. Now, if you have other welding processes that we'll talk about later, you can't do that. Everything needs to be clean on the first place. So what else there is to say here? So we essentially have that consumable here that forms into the slag. We have the metal that forms the fusion zone. We have control of speed, and all the electrical control defines how much heat you're providing. One of the very, very common way, we'll skip this for today, go back to it. The most common way for structural steel where the welding becomes a problem, so we're talking here about low-strength steel, is if you try to go too fast and you end up not melting through the base metal. So this is a relatively complex geometry, and I'll draw it here. Let's see. It's a round bar, and we can come back to it later. That's bent this way, and it goes over a tube that's rectangular. So what you see, this is solid, this is hollow. We're looking at the tube here and the bar, and this is the weld. You can see that the weld bead did not really penetrate into that tube, and that makes for a very low ductility joint. They had a lot of problem with this, and we'll go back to that on Wednesday. Tomorrow, Professor Eager is lecturing. This week, it's me on Wednesday and Professor Eager Tuesday, Thursday, and Friday. I sent the announcement. So, thank you.